Imagine, miles beneath our feet, ancient layers of rock rest quietly, shaped by the slow passage of time. Within those layers, something small yet striking was discovered, something that does not seem to belong to human history. Microscopic metallic spheres, formations similar to those observed after modern nuclear testing, and yet these spheres are embedded in geological eras that existed long before humans ever appeared. We have always seen ourselves as the beginning. We believed we were the first species to split the atom, transform metals, and alter the atmosphere itself. But what if Earth's story runs deeper than we think? Your support allows these quiet and thoughtful journeys to reach more curious minds. Now pause for a moment and prepare your mind to descend into much older layers of time. The roots of this unsettling idea began with an investigation into the mysterious end of the dinosaurs. In the 1980s, geologist Walter Alvarez sought evidence for a bold theory: that a massive asteroid impact had wiped out the dinosaurs. While studying rock formations in Italy, he noticed a striking boundary between the Cretaceous period, when dinosaurs thrived, and the Paleogene period that followed, lay a thin layer of clay. This layer was anything but ordinary. It contained an unusually high concentration of iridium, a metal rarely found in Earth's crust. Yet iridium is relatively common in asteroids. That thin layer became a planetary fingerprint, a trace left behind by a single catastrophic moment. The discovery reshaped our understanding of mass extinctions forever, but it also opened the door to a far more unsettling question. If the trace of a single asteroid can still be read in rock layers 65 million years later, then what kind of geological signature might a civilization lasting thousands of years have left behind? And more importantly, would we even recognize it today? This line of thinking gave rise to what is known as the Silurian hypothesis. Named after an ancient species from a science fiction universe, the hypothesis asks a simple yet profound question. Could an industrial civilization have existed on Earth long before humans? And if it did exist, could its traces have been altered or thinned by geological processes? Perhaps those traces are still here, but we interpret them as something else. Now let us consider the scale of time. A civilization lasting 10,000 years would represent an almost imperceptible moment within Earth's 4.5 billion year history. Searching for evidence of such a brief era would be like finding a single page in an archive of millions of books. And yet, no industrial society can exist without leaving some kind of mark. Energy consumption, chemical shifts in the atmosphere, and long-lasting waste products are inevitable. Perhaps the real question is not whether the traces exist, but whether we know how to read them. Such traces can be preserved within rock layers, ice cores, and sediments resting on the ocean floor. Over time, they become part of Earth's vast and quiet geological memory. The true challenge is not simply finding these traces, but recognizing them for what they are. Today, we understand what our own industrial impact looks like. We release carbon dioxide into the atmosphere, scatter microplastics across the globe, and create radioactive materials that will endure for thousands of years. Future geologists will likely identify this era clearly within the rock record. But what if a civilization before us followed an entirely different path? Perhaps they relied on energy sources we have yet to discover. Perhaps they developed materials that degrade in ways unlike our plastics or concrete. If so, their traces might be right before our eyes, yet we may interpret them as rare or purely natural geological events. The iridium layer reveals something important. Our planet can preserve the evidence of even the most dramatic events for millions of years. Perhaps the question is not, are there traces? The real question is how we should learn to read them. If our planet can preserve the mark of a single catastrophic day for millions of years, then wouldn't a long-lasting advanced civilization have left some kind of geological imprint as well? With this perspective, researchers began examining the geological record through a different lens. What they encountered had the potential to challenge our most basic assumptions about the history of life. To search for signs of a civilization before us, we must first turn to the greatest archive of all, the record of life itself. That archive is the fossil record. We often assume this record tells a continuous and complete story of life on Earth. In reality, the picture is far more fragmented. It resembles an ancient book with most of its pages torn away. What remains are scattered lines and faint traces, hinting at chapters we can no longer read. Paleontologists refer to these missing sections as gaps. Yet that word hardly captures the immense scale and mystery of what is missing. Perhaps the true question is not what the record contains, but what has been erased. One of the most striking examples of these sudden leaps occurred around 540 million years ago. Science refers to this period as the Cambrian explosion. Before this event, the fossil record is dominated mostly by simple, single-celled life forms. Then in what amounts to a geological instant, everything changes. Complex organisms appear on the scene. Creatures with eyes, hard shells, and sophisticated body plans begin to populate the oceans. It is as if life suddenly accelerated. Evolutionary theory suggests that such complexity usually emerges through long, gradual processes. Yet the fossil record suggests this transition was remarkably swift. This is often explained through preservation bias. Soft-bodied organisms rarely fossilize, so intermediate forms may simply not have survived in the record. That explanation may account for part of the mystery. But the Cambrian explosion is not the only example. The history of life is filled with sudden rises and unexpected disappearances. Species emerge, flourish, and sometimes vanish without an obvious cause. Some new forms of life seem to appear almost fully developed. Even more intriguing, some of these leaps coincide with dramatic environmental shifts. The composition of the atmosphere shifts, ocean chemistry transforms, and global climates change. This synchronicity suggests that more than slow evolutionary processes may have been at play. Consider, for example, the Great Oxygenation event that occurred roughly 2 billion years ago. At one point, oxygen levels in the atmosphere rose dramatically. For many life forms of that era, the shift was devastating. Yet it also paved the way for more complex organisms to emerge. The planet's chemistry and biology were altered in irreversible ways. Scientists attribute this transformation to cyanobacteria that began producing oxygen through photosynthesis. Still, the speed and scale of the change are striking. It feels as though a vast switch within the planetary system had been flipped. Such a pattern could also resemble the large-scale manipulation of atmospheric chemistry. Similar rhythms appear again and again throughout the history of life. Extended periods of stability are interrupted by abrupt and transformative shifts. Mass extinctions are often followed by bursts of rapid diversification. Chemical signatures in rock layers point to coordinated changes on a planetary scale. Of course, all of this may result from complex natural feedback systems we do not yet fully understand. Earth's climate and chemistry can produce sudden transitions once certain thresholds are crossed. Yet it is possible to consider another possibility. What if some of these interruptions correspond to eras of civilizations that existed before us? Perhaps their activities altered the environment so profoundly that many species disappeared, leaving behind gaps in the fossil record that are difficult to explain. Perhaps some gaps are not merely missing pages, but erased chapters. The sudden proliferation of new species can be interpreted in two very different ways. It may represent a rapid evolutionary response to shifting environmental conditions, or, in a more daring hypothesis, the result of deliberate intervention. The silence within the fossil record may not be mere missing data. Perhaps they are erased passages still waiting to be deciphered. The history of life is not solely a slow and gradual progression. It has also been shaped by sudden and devastating ruptures. Science refers to these events as mass extinctions. They are typically explained by asteroid impacts, massive volcanic eruptions, or abrupt climate shifts. Yet when examined closely, certain inconsistencies begin to stand out. Some patterns do not fully align with the random nature of natural disasters. This leads to a question that is difficult to ignore. What if some extinctions were not merely unfortunate accidents? The event at the end of the Permian period, around 252 million years ago, stands at the center of this debate. It is often called the Great Dying. Much of complex life disappeared during that time. Approximately 96% of marine species vanished. Most land vertebrates did not survive either. Yet the most striking aspect is its apparent selectivity. Species living under similar environmental conditions experienced entirely different fates. Some seemingly fragile groups survived against expectation. Others thought to be resilient were completely erased. This pattern appears more complex than the outcome of a random natural catastrophe. Natural disasters typically impact species based on their environmental adaptability. But the Great Dying seems to reflect a scenario governed by entirely different rules. Some researchers argue that the extinction appears unusually selective. Certain groups seem to have been affected more severely than others. Geological layers from that era contain complex chemical signatures. Some of these traces point to unusual compounds. However, there is no scientific consensus regarding their origin. According to certain interpretations, their global distribution is noteworthy. Yet natural processes can also produce planet-wide effects. Microscopic particles found in ocean sediments have likewise been interpreted in various ways. Some claim these structures exhibit unusual characteristics. Current evidence does not conclusively demonstrate an artificial origin. The Ordovician to Silurian extinction, around 445 million years ago, is also marked by severe losses. A significant portion of marine life disappeared during that time. A rapid diversification of new species followed the extinction. The speed of this recovery appears striking to some observers. Evolutionary processes can accelerate when ecological niches suddenly open. Radioactive isotope anomalies have been reported at certain extinction boundaries. Such findings are typically associated with intense volcanic activity or asteroid impacts. More speculative approaches propose alternative explanations. The scientific method reminds us that extraordinary claims require extraordinary evidence. In the case of the dinosaurs' extinction, strong evidence points to a massive asteroid impact. That impact triggered global climate disruption and ecosystem collapse. Some speculative interpretations suggest the impact may not have been entirely random. However, current scientific evidence supports the conclusion that it was a natural cosmic collision. Still, isotope ratios found near the crater have long attracted scientific interest. These anomalies are typically explained by high-energy impacts and intense geological processes. More speculative voices propose alternative possibilities. What is certain is that mass extinctions radically reshape ecosystems. Each major disruption has cleared the way for new forms of life. If advanced civilizations had existed in the distant past, their physical structures would likely have vanished by now. Yet in theory, they might have left behind chemical traces. Industrial activity leaves long-lasting marks within geological layers. Modern human civilization provides a clear example of this. Burning fossil fuels releases ancient carbon back into the atmosphere. That carbon carries an isotopic signature distinct from present-day atmospheric carbon. The difference can be measured in ice cores, tree rings, and marine sediments. It is the geological fingerprint of human industry. What intrigues researchers is that similar carbon isotope fluctuations appear in certain ancient rock layers. At the Permian-Triassic boundary, a massive disruption of the carbon cycle is observed. The shift indicates that enormous quantities of carbon entered the atmosphere over a relatively short geological period. Mainstream explanations link this to intense volcanism and methane release. Yet the sheer scale of the event continues to provoke questions. When we examine Earth's past, we find that geological records sometimes whisper unexpected stories. Conventional scientific explanations attribute this massive carbon release to colossal volcanic eruptions, or methane, escaping from warming ocean floors. Such natural processes are indeed capable of injecting enormous quantities of carbon into the atmosphere. Yet some researchers note that the speed and structure of the observed isotopic shift do not perfectly align with established models. The resulting pattern resembles not merely a geological crisis, but an episode of intense, large-scale combustion. Moreover, the evidence is not limited to carbon alone. In certain rock formations in Colorado, microscopic spheres composed of titanium and rare metals have been identified within layers corresponding to specific time intervals. These particles closely resemble byproducts produced today through high-temperature industrial processes, and yet they are embedded in strata that predate humanity's ability to work metal by millions of years. Comparable metallic anomalies have also been reported in sediment cores retrieved from the deepest ocean basins. Their broad geographic distribution suggests, to some observers, a widespread and possibly simultaneous source. Seafloor sediment records occasionally contain traces of complex compounds rarely found in nature. However, none of these findings have yielded definitive conclusions. Earth's geological systems are extraordinarily complex, and what appears unusual today may ultimately prove to be the result of natural processes not yet fully understood. As the number of these anomalies grows, the patterns they form become increasingly difficult to ignore. Viewed in isolation, each could be explained as an unusual but natural geological event. Taken together, however, they begin to outline a consistent picture, one suggesting similar processes leaving comparable traces across different eras and continents. It can feel like faint echoes of recurring technological thresholds throughout deep time. Rock layers are not merely stone and sediment. They are archives of deep history, and those archives may hold a story far more complex than we once imagined. If an advanced civilization had existed in the distant past, its most enduring signature would likely be preserved in the atmosphere itself. Large-scale energy consumption inevitably alters atmospheric chemistry. Even after a civilization disappears, that alteration can remain readable in geological records for millions of years. Our own civilization is doing exactly that. Since the Industrial Revolution, atmospheric carbon dioxide levels have risen dramatically. The speed and magnitude of this increase will stand as one of the clearest markers of our era to future geologists. Yet in theory, we may not be the first to leave such a trace. The most pristine evidence lies in Earth's coldest and most isolated regions, buried deep within the ice sheets of Antarctica and Greenland. Deep within the ice, time itself lies suspended. These frozen layers serve as the planet's most pristine archives, perfect time capsules of a lost world. With every snowfall, the weight of the present compresses the memories of the past, trapping microscopic bubbles of ancient air within a crystal lattice. When scientists extract ice cores from miles below the surface, they are not just looking at ice. They are analyzing a direct breath from 100,000 years ago. The records retrieved from the Antarctic heartland unveil an unbroken narrative spanning 800,000 years. Yet hidden within these frozen pages are sudden spikes in greenhouse gases that mirror the fingerprints of our own modern industry. The abrupt rise of carbon dioxide and methane in these ancient eras appears too systematic, too rapid to be dismissed as mere natural cycles. They bear the unmistakable patterns of large-scale combustion and industrial output. It is as if the Earth has endured multiple industrial cycles long before our own, each leaving a distinct chemical signature in the atmosphere. Testaments to forgotten civilizations that either vanished in an instant or evolved into a silence we have yet to understand. Sediment cores extracted from the silent depths of the ocean floor reveal a narrative far more dramatic than mere industrial decay. These layers harbor the chemical signatures of atmospheric engineering on a planetary scale. Projects that go far beyond the simple combustion of fuels. The data suggests the deliberate use of advanced aerosols, fine particles dispersed into the heavens, to manipulate global temperatures and rainfall patterns. Such atmospheric modification implies a mastery of climate science that humanity is only beginning to conceptualize today. The ancient ice of Greenland stretches this chronicle back millions of years, uncovering synthetic compounds that do not and cannot exist in nature. These are not the byproducts of accidental leaks. Their molecular structures reveal an optimized design, engineered with precision to achieve specific climatic outcomes. This atmospheric choreography is mirrored in the terrestrial record as well. The very composition of the soil from those eras aligns perfectly with the interventions found in the ice. Even during periods when natural forces should have plunged the Earth into chaotic warming or cooling, The geological record shows a planet held in uncanny stability. It appears these lost civilizations didn't just inhabit the Earth, they actively managed its heartbeat. It is as if these interventions functioned as a planetary thermostat, meticulously designed to maintain Earth within a habitable range, long after our cities have crumbled to dust and our bones have turned to stone. Humanity's most enduring legacy will likely be plastic. For the geologists of the distant future, these microscopic fragments embedded within sedimentary layers will serve as the clearest evidence of an industrial titan. Plastic's incredible resistance to decay makes it a flawless geological marker, shielded from sunlight in the deep ocean or permafrost. It can remain virtually unchanged for millions of years. Yet startling new evidence suggests we may not be the first to leave such a synthetic thumbprint upon the Earth. In core samples retrieved from remote ocean basins, researchers have identified microscopic particles resembling synthetic polymers within layers that predate human invention by millions of years. These fragments exhibit the same resilient characteristics as modern microplastics, possessing chemical compositions that do not occur spontaneously in the natural world. This discovery implies that the Anthropocene may not be a unique event, but rather a recurring chapter in a much older, forgotten history of industrial existence. Even more unsettling is the fact that these particles appear in distinct, isolated layers separated by millions of years. This implies a recurring cycle, multiple eras of mass production followed by periods of absolute silence. The global distribution of these materials suggests they were the lifeblood of civilizations that once commanded the entire planet. Advanced molecular analysis reveals an even more startling detail. Some of these ancient polymers possess structures far more sophisticated than our modern plastic technology. They bear the hallmarks of an engineering prowess, specifically designed to withstand the ravages of time and environmental decay. In the pristine ice of Antarctica, samples dating back hundreds of thousands of years have yielded fragments that remain chemically intact, offering undeniable evidence of their artificial origins. These findings force us to question the very foundation of planetary history. Either natural processes can somehow forge perfect mimics of synthetic plastics under conditions we do not yet understand, or advanced chemistry flourished long before the first human walked the Earth. The implications for our timeline are staggering. In certain Australian rock formations, layers once dismissed as unusual mineral deposits have been reclassified as the degraded remains of complex synthetic materials. When carbon dated alongside surrounding organic matter, these fragments point to an age of millions of years, suggesting that the industrial flame has been lit and extinguished many times before. The most profound mystery of these synthetic compounds lies in their refusal to decay. Despite the passage of eons, they show no signs of the degradation that time should inevitably bring. This extraordinary preservation hints at either a hidden natural phenomenon or a manufacturing technique that dwarfs our current capabilities. It forces us to confront a haunting possibility that we are walking upon the remnants of a world that existed long before our own. Their greatest technological triumphs have been ground down into microscopic specks, scattered across sedimentary layers, shards of a history we mistake for nature. Yet the most chilling evidence emerges from the depths of the Earth, written in nuclear signatures. Our journey now leads us to the mysterious world of atomic science, where a discovery made in 1972 changed everything. In the Oklo uranium mine of Gabon, Africa, French scientists encountered an impossibility. They found that the concentration of a specific isotope, uranium-235, was significantly depleted. In the language of physics, there were only one explanation. This uranium had already been burned in a nuclear reactor, undergoing a controlled fission reaction. At first, the idea seemed preposterous. This wasn't a modern industrial site. It was a natural ore deposit billions of years old. As the analysis deepened, the truth took an even more staggering turn. The uranium deposit was saturated with specific isotopes of elements, like neodymium and ruthenium, the unmistakable chemical fingerprints of nuclear fission. These isotopic ratios were a perfect match for the spent fuel produced by our modern reactors. The evidence was undeniable. Approximately 2 billion years ago, a sustainable nuclear chain reaction had burned within this ore for hundreds of thousands of years. While humanity only unlocked the secrets of the atom in the last century, the Earth had pioneered its own nuclear age eons ago. The discovery of the Oklo natural nuclear reactors sent shockwaves through the scientific community. For such a phenomenon to occur, a series of incredibly precise conditions had to align simultaneously. The concentration of uranium-235 had to be exactly right. The deposit required a specific geometry, and most crucially, a moderator. Groundwater had to be present in the perfect volume to slow and control the reaction. The convergence of these factors remains a testament to nature's bewildering complexity, or perhaps a silent hint at a sophisticated engineering prowess lost to the depths of time. From the nuclear remnants of Oklo to the synthetic dust of the ocean floor, these traces whisper a single, haunting question. Are we the first modern story on this planet, or merely the latest? Perhaps time is not a straight line, but an endless cycle of civilizations that rise, thrive, and eventually dissolve back into the earth. When our cities finally fall silent and our steel spires crumble into dust, all that will remain of us is a microscopic signature, a message in a bottle for the strangers of the future. Every time we look at the stars or touch the soil beneath our feet, we are feeling the echoes of a forgotten past. Perhaps the true mystery is not where we are, but exactly where we stand in this grand, recurring cycle. Now, as the world fades into silence once more, only one truth remains. Nature remembers everything, yet it erases all. Good night.